So in this lecture, we are going to discuss on a proof for the Weierstrass approximation theorem. I already explained what is the meaning of Weierstrass approximation theorem into the previous lecture. So the theorem states in this manner: let f be a continuous function, then prove that there exists a sequence of polynomial Bn of f. What is Bn of f? Is a Bernstein polynomial. So I can say sequence of Bernstein polynomial such that Bn f is converges to f uniformly on closed interval 0, 1. This result is also true for any interval AB. But for that, you have to define a Bernstein polynomial for the function f, which is defined over the interval AB. So slightly modification you have to do for the Bernstein polynomial. What is Bernstein polynomial? We also discussed in the previous lecture. Okay. So let us give the proof for that. See, here very fundamental things we are using, which we have proved for this course, that if f is a continuous function on closed interval AB, or sorry, closed interval 0, 1 here in particular, that means f is a function which is defined over the compact set. F is defined over the compact set and the function is continuous. So the function has to be bounded. Therefore, I can say that f is bounded function on closed interval AB due to the compactness as well as continuity, which we have this. And so we can say that, or we can say consider some m, which is the supremum of this fx, x belongs to closed interval 0, 1. See, here we have heavily used the boundedness of the function. Okay. So the question arises, that is the first one of the point to do the research on it. If I can replace this interval with open interval, what are the drawbacks? Can we able to prove this one, or whether this result is true for instead of open interval, if I can write down the closed interval, can it be theorem is true? If not, you have to find out the counter example for that. Okay, so that is one of the key point I have to say here, that instead of closed interval, if I can take open interval, what will happen? If the theorem is true, then you have to prove for that. If not, you have to give the counter example for that. Okay, and I will tell you the theorem is not true. So kindly find out what are the counter example for that. That means in that case, we will not have any polynomial which converges uniformly to that function. And also we have given f is continuous on a compact set. So we also did one result that if f is continuous on a compact set, it is automatically uniform continuous. So that also we say, since f is uniformly continuous on closed interval 0, 1, due to it is continuity, it is uniformly continuous. For given epsilon greater than 0, there exists a delta greater than 0 such that for every xy belongs to 0, 1, mode of x minus y is less than delta implies mode of f of x, f of y is less than epsilon, where this delta is only depends on epsilon, not on x. I can call this is the first statement. Now from the Bernstein polynomial discussion, what we have achieved is this, if I start with what is actually I have to prove that Bn of f minus fx is less than epsilon. That is, or I can say the distance between them is very less. So we need to measure what is Bn of f at x minus fx. So we'll start with this thing. Consider this. Now, as per the definition of Bn of f, we can say that is k running from 0 to n, nck x power k into 1 minus x power n minus k into f of k by n minus fx. Minus fx into 1 I can write. Now, what we have did is Bn of 1 at x will be 1. So instead of this 1, we will substitute Bn at 1. Bn at 1 is exactly summation k running from 0 to n nck x power k 1 minus x power n minus k. So as per that, this is k running from 0 to n nck x power k 1 minus x power n minus k in bracket f of k by n minus f of x. That is the one, value of 1 is there. So we have substituted and then common out this quantity. Now we have to looking at this expression. I will call this as a statement number 2. Now let us looking at this quantity. That means what will happen if k, see, if I want to use the first statement, that is x minus y less than delta, implies that f of x minus f of y is less than epsilon. That means k by n minus x should be less than delta. Then we can say this is less than epsilon. So if those value where k by n minus x is less than delta, we don't have any problem. So, and this summation is starting with 0 to n. So I'm just dividing this summation into two parts. Whenever this k by n minus x is less than delta and k by n minus x is greater than or equal to delta. So what I will do is for fix x belongs to 0, 1, S1 we can define as k, where k by n minus x is less than delta, and S2 we define as all the k such that k by n minus x is greater than or equal to delta. Now this summation is divided into two parts. Either k is in this or k is in this, because it starts with 0 to n. So now for those k which are in S1, what we can say as per this statement 1, due to the statement 1. So from 1 we can say that f of k by n minus f of x is less than, I may adjust that epsilon by 2. So that is, I'm adjusting, this is epsilon by 2, because this summation is divided into two parts. K belongs to S1 plus k belongs to S2. So for S1 we have this. Hence the summation which is belongs to S1 is nck x power k 1 minus x power n minus k f of k by n minus f of x. The modulus of this whole quantity is less than or equal to summation k running from or belongs to S nck x power k 1 minus x power n minus k mod of f of k by n minus f of x, and that is less than epsilon by 2 summation k running from 1 to S nck x power k 1 minus x power n minus k, because indeed it is independent, epsilon is independent of k. Now this is again I can say less than or equal to epsilon by 2 summation k running from 0 to n. So I am adding those terms which are not here in between 0 to n. I am adding all of them. So it is obviously it is greater than, sorry, less than or equal to this quantity. And so this is equal to epsilon by 2 because this quantity is 1 due to the first moment, sorry, 0 moment. So finally what we got is for x belongs to S1, dn of f at x minus fx mod of that is less than epsilon by 2. If I call this is as 3. Those x which are in this, we have this. Now for k is in S2. What will happen? K by n minus x is greater than or equal to delta we have. So this will implies k minus nx upon n is greater than or equal to delta, which implies k minus n is greater than or equal to n square delta square. And k minus nx square we already calculated in the previous lecture. So what we have is when now the summation k running from S2 mod of f of k by n minus f of x nck x power k 1 minus x power n minus k is less than or equal to 2 times, because this quantity is less than or equal to f of k by n plus mod of f of x, and we have taken that f has a maximum value as m, so that is less than or equal to 2 times m k belongs to S2 nck x power k 1 minus x power n minus k. Now still this is further less than or equal to due to this n square delta. So I can say due to this one it is k by n whole square by n square delta square is greater than or equal to 1. So 1 is less than or equal to this quantity. So I can just multiply and divide by this quantity here. So this is less than or equal to 2 by summation k belongs to S2 k by n x whole square upon n square delta square, because I can say 1 is less than or equal to due to this quantity nck x power k 1 minus x power n minus k. So that is further less than or equal to 2 by n square delta square is independent of k, so I can write down is outside, and adding more terms from k running from 0 to n, k minus n x square nck x power k 1 minus x power n minus k. And in the previous lecture we have discussed that k minus nx whole square will be less than or equal to n by 4, which we have proved for Bunstein polynomial. You can see that in the last statement, and also here, that is this quantity k minus nx square is less than or equal to n by 4. So due to that we can write this is less than or equal to 2m n square delta square into n by 4. N is cancelled out, 4 will get cancelled. So we can say this is equal to m by n to n delta square. I can say this is less than epsilon provided that your n is greater than m upon epsilon delta square, which is your n0. This will be your n0. So we have to choose n0 belongs to n such that n0 is the m plus epsilon delta square plus this box is a greatest integer function plus 1. So I can say where box of y denote the integral part of y. Okay, and you can just observe this n0 which we got will not be depends on x, it only depends on epsilon. Okay, and I will call this as the statement number 4. So what is the statement 3 and 4? Using the 3 and 4, now for any given epsilon greater than 0, there exists n0 belongs to n. What is n0 is this, such that, or I can say maximum of this n0 and the previous one which we have for delta which we have taken, fx at x minus fx is less than or equal to summation k running from 0 to n mod of f of k by n minus f of x and ck x power k 1 minus x power n minus k. This is less than or equal to divide into the two summations, that is k running from belongs to s1 mod of f of k by n minus f of x and ck x power k 1 minus x power n minus k plus k belongs to s2 f of k by n minus f of x and ck x power k 1 minus x power n minus k. So as for 3 and 4, this is less than epsilon by 2 plus epsilon by 2 for every n greater than or equal to n0, and hence this n0 is depends only on x. So we can say that Bn of f converges f uniformly as n tends to infinity on closed interval 0 1, and which completes the proof of Weierstrass approximation theorem. Now, what are the scope of doing or to generalize this statement? What is this statement says that if f is a continuous function, then there exists a sequence Dn, where the sequence is a polynomial sequence such that Dn of f is tending to infinity. Sorry, Dn of f is converged to f uniformly. So there are lots of scopes here. Why it is only Bn of f? That means why it is the only Bernstein polynomial is there, is exist. So there are different various kind of polynomials are exist there, sequence of polynomials. Among those polynomials, sequence of polynomials, which one is the best one? So that the error term between these two is very, very small. That is the one scope of doing the further research on it. The another one is we have taken a class of continuous function. Instead of this continuous function, can we do the integrable function? If f is integrable, and then there are different various kind of integrabilities there, Riemann integrable, Lebesgue integrable, and furthermore, there are other integrations are there. So different class of functions you have. For example, functions of bounded variation. Suppose f is a functions of bounded variation. Can we have some sequence of polynomial like this, such that that sequence of polynomial will converge to the function f? So all sort of the areas where you can extend this Weierstrass approximation theorem, and many people in the world are working on it, and there are lots of huge of application of this Weierstrass approximation theorem in computer science. Okay, so if you have any question, you can ask.